Okay, in this video I'm going to talk to you about pressure and mostly just give the definition for it. So pressure is the force that's delivered by a gas through its collisions per unit area. So if we imagine, say, a balloon or something like that, and there's all these gas molecules inside the balloon and they're all flying around colliding into the side. When they hit the side, they hit it with some sort of force. We'll call that F. So every time they hit that side, they push the side outward, they deliver force. Pressure refers to the amount of that force per unit area. So if we imagine the area that it's hitting on the side of the balloon, how much force is being delivered in that given area? So how does it relate to a few things here? Well, how does it relate to temperature? Well, as the temperature goes up, we know that that really means that the speed, on average, of the gas molecules is also increasing. Which means that when they hit, they'll be going faster, which means they'll deliver more force. So if we increase the temperature, we get more force. The unit area hasn't changed, so we get more pressure. Alternatively, with volume, let's imagine again two balloons here. Here's a little balloon, here's a great big balloon. The area, let's say they had the same number of gas molecules in them. When these particles hit the side of the balloon, they have a very small area to hit over here. So small volume means small area. Alternatively, in this large balloon, when they hit the sides, they have to cover a very large area. What that means then is that as volume is increased, surface area is also increased. Since pressure is the force per unit area, if we make the area go up because it's on the denominator, the pressure will go down. So as volume increases, pressure decreases. Both of these arguments are assuming that the number of particles is fixed. Now, an interesting aspect of pressure that we take for granted is the atmospheric pressure. If we imagine the Earth, it is a very thin atmosphere. But still, by our standards, it's quite high, because that still is a very significant amount. What that means then is if you're sitting on the Earth, then all of this air is sitting on top of your head. And so the weight from these gas molecules sits on these gas molecules, and so on and so forth, all the way down. So all the weight I wrote mass, but I really should say weight. Of these gas molecules is resting on the gas molecules at the bottom. And again, I should be saying particles. What that means then is that there's a lot of force pushing down on these gas molecules. So when they run in to anything down here, they're going to have a lot of force to deliver on that collision. So that force, again, when we consider it per unit area, we call pressure. And the pressure associated with the entire atmosphere sitting on top of us is called the atmospheric pressure. Now, force is typically measured in a unit called the Newton, and area is typically measured in meters squared. So somebody came along and made up a unit for pressure in general called the Pascal, 1 Pascal. And atmospheric pressure is so large that it is 101,300 pascals, or more simply written, 101.3 kilopascals. This is an average value at sea level. It varies depending on how high you are or based on the weather conditions around you at the time. One thing that's interesting about this is the pressure that keeps water from boiling. So this pressure is sitting on top of your glass of water. And if you imagine that those gas molecules hitting the top of your water, those are the ones that keep the water vapor from being able to form bubbles in your glass and keep that water all settled at the bottom of the glass. Also interesting here is that if you go up to very high altitudes, like on the top of Mount Everest, you can see a very substantial decrease in the overall atmospheric pressure. This leads to a few interesting things. One, water will actually boil at lower temperatures up there because there's not as much atmosphere keeping the water from boiling. But also, the amount of oxygen in the air will be reduced greatly because the gas isn't pressurized, isn't compressed in the same region. This is why you have to if you're going to try and climb Mount Everest, you have to go up a certain ways and get acclimatized to the lower air pressure. But on top of that, you also sometimes will take oxygen tanks to supplement the amount of oxygen that you're actually going to receive up at those high altitudes. So that's what pressure is, the amount of force delivered by colliding gas molecules per unit area, how it relates to temperature and volume, and why our atmosphere delivers a certain amount of force per unit area or an atmospheric pressure on us, depending on the weather conditions and where we are on the Earth.